In the previous lecture, we introduced Newton's third law of motion, and we applying it to to this context of striking nail with a hammer. We argue that when the hammer hits the nail, the hammer exerts a force on the nail, which is shown in the sketch right here. That arrow represents that force. And what Newton's third law says is that the nail, in fact, in turn, exerts an equal and opposite force on the hammer. That's this arrow out here. Equal and in magnitude, opposite in direction. Okay. So when one object, so what we argued there was, and a simple way to say it is that the forces come in pairs. So when one object exerts a force on another object, the other object exerts an equal and opposite force on the first object. Now, if you read Newton's third law, it sounds pretty straightforward. I mean, it seems there's not much. It's pretty straightforward statement and quite simple. But when you apply it to situations, you need to be a bit careful when you apply Newton's third law to situations. So here are a few comments on the third law. There are two remarks that I want to make before we proceed. One is what we said before. The forces come in pairs, which we call action-reaction pairs. What we call the action and what we call the reaction force is left up to us to decide. But the second point, which one tends to forget, is that action-reaction pairs act on different objects. So let's look at a simple situation. You've got a book at rest on a table. And if I were to ask you to draw a free body diagram of the book, you would say, well, there is the weight of the book acting in the downward direction, and this is the force that the earth exerts on the book. And here is the normal force that the tabletop exerts on the book. And since this book is not accelerating, these two forces are equal in magnitude and opposite in direction. So let's state that. So we observe that in this case, W and N are equal in magnitude and opposite in direction, by which I mean in magnitudes these two forces are equal, and opposite in direction, exactly opposite in direction. So based on that, one may conclude that hence they are action-reaction pairs. Okay. So you might think, oh, well, they form action-reaction pairs, but now here's where you got to be careful. That would be a wrong conclusion. Let me write it in a thick font. That's wrong, okay? So just because two forces are equal in magnitude and opposite in direction do not make them action-reaction pairs. Again, going back to these remarks that I wrote down, notice we said that action-reaction pairs act on different objects. These are two forces acting on the same object, so they could never be action-reaction pairs. So the question then becomes, well, you've got the weight of the book, which is the force that the earth exerts on the book. Earth is pulling the book down with that force. So a natural question to ask would be, what is what is the reaction force to the weight of the book? Okay, so what is the corresponding pair? What is the corresponding force which form the action reaction pairs if it's not the normal force? And so now here is the situation that we're describing. Now let's look at the situation carefully. You've got the earth, you've got a picture out here where you got the earth, and you've got the earth exerts a force on an object. In this case, it's a ball. The earth is pulling down on this object. And Newton's third law says that, well, if the earth exerts a force on the object pulling it down, then the object, in this case the ball, exerts an equal and opposite force on the earth, pulling the earth up. Okay, so the action reaction pairs that we are talking about here are in fact these two forces. Okay, these are action reaction pairs. Every object that you have near the earth's surface, just as the earth pulls every object near its surface in the downward direction, these objects are also exerting a force on the earth, pulling them in the upward direction. Okay, and then a question you might ask is, well, if these two forces, if every object is pulling the earth up, if this ball is trying to pull the earth up, why is it that the ball is always the one that's accelerating down to meet the earth and not the earth moving up to meet the ball? Well, the reason for that now is Newton's second law, which says that now if you compare the masses of the two objects, since the mass of the earth is so much greater than the mass, in this case, of the ball, the acceleration of the earth is so much less than the acceleration of the ball. Okay, so you do not measure the acceleration is so minuscule that you couldn't measure it. Okay. But back to the original statement. So when you are deciding what are action reaction pairs, notice you got to be a little careful analyzing the situation. Notice action reaction pairs are two forces that are acting on different objects. So the weight of the object is the force that the earth exerts on the ball, and the reaction pair to that would be the ball exerting an equal and opposite force on the earth. Let's end with a few conceptual questions on Newton's third law. Here's one. A mosquito runs head-on into a truck, which is true during the collision. So obviously, there is no measurable effect on the truck, but unfortunately for the mosquito, it never survived that collision. So in this situation, again, according to Newton's third law, whatever force that the truck exerts on the mosquito, well, the mosquito exerts the same force on the truck. Okay, and we'll come back and talk about this. Here's another question. A semi-trailer truck crashes all the way through a wall, so it again completely destroys the wall. Since the wall collapses, the wall sustains a greater force than the truck does, and pretty much, let's say that nothing happens to the truck, so it means that the wall experiences a greater force. This conclusion again is false, because Newton's third law says that the forces are equal. Now, the reason why in this case, in the previous situation, the mosquito died, and in this case, the wall collapsed, is got something to do with the structure or the structural integrity of that particular object. But as far as forces go, the forces acting on both these objects, in this case the truck and the wall, in this case the truck and the mosquito, are the same. Okay.